In this lesson, I just wanted to give a quick overview of the rules of exponents when we're operating with them. Hopefully this is a review topic for you. If not, then be sure to read P.2 again in some more detail so that way you have a better understanding. It's going to keep coming back. The first is our product rule. When we're multiplying exponential expressions with the same base, we add the exponents. So b to the m times b to the n equals b to the m plus n. For our quotient rule, when we're dividing exponential expressions with the same base, we subtract the exponents. When you multiply, you add your exponents. When you divide, you subtract your exponents. Just two quick comments on this is that they have to have the same base. So if you're multiplying an x squared and a y to the third, you do not do anything with those exponents. They have to have the same base. Also, the base stays the same after the operation is complete. So if you look at the product rule, b to the m times b to the n equals that b, that base is still there. It's just your exponent that ends up changing. So just a few quick examples using the product and the quotient rule, so that way we make sure that we have that understanding. If I have x to the 13th times x to the 25th, that means I'm really doing x to the 13 plus 25. Again, that x still stays there. We keep the same base, so 13 plus 25 is just going to end up being 38. So your answer, if you were multiplying those, would just be x to the 38. Now, this is where sometimes students get confused, is that if we have a number as a base, it's still going to be the same process. So if we have 3 squared times 3 to the third, that 3 is still staying a 3. And we're doing 3 to the 2 plus 3 to get to 3 to the 5th, which is just equal to 243. So I realize it might seem a little counterintuitive from what you're used to. If you see 3 times 3, you might think to do 9, but it's not. Same process we did with our x stayed an x when we were multiplying. Our 3 stays a 3. And that 3 to the 5th, you can either multiply out 3 times 3 times 3 times 3 times 3, or you can use your calculator and use the caret button where you would have 3 raised to the 5th power and just type it in that way to get the 243. With our quotient rule then, we have y to the 13th divided by y to the 5th. They're both the same base. With our quotient rule, we subtract our exponents, so we would have y to the 13 minus 5. So 13 minus 5 is just 8, so this stays then y, and we raise it to the 8th power. Again, with our numbers, here we have a base of 10, so we're still dividing, but we keep that same base. So we're going to have 10 raised to the 5 minus 2. 5 minus 2 is going to be 3. So we have 10 to the third power, which would just be 1,000. So again, even though we have our numbers, just make sure that you're keeping that same base. Next, we have our zero exponent rule. If b is any real number other than 0, b to the 0 is equal to 1. So just that idea that a number other than 0 raised to the 0 power is equal to 1. The good question is, where does this actually come from? Well, if we think about if I had something like 2 to the third over 2 to the third. Well, 2 to the third is 2 times 2 times 2, which is 8. So we would have 8 over 8. Well, we know that 8 over 8, 8 divided by 8, is just 1. But if I use my quotient rule, I would have 2 to the third over 2 to the third. Our quotient rule says that when we divide, we subtract our exponents and we keep the base, so we keep the 2, and then we would be doing 3 minus 3. Well, 3 minus 3 is 0, so we'd be left with 2 to the 0. So we started off with equivalent statements, 2 to the third and 2 to the third. We solved it differently, and we got this idea that 2 to the 0 and 1 have to be equal to each other, since we started with an equivalent statement and we solved it 2 different ways. So any real number other than 0 raised to the 0 power is equal to 1. So if I had something like x to the 0 equal to 1, no work. Even if I had something like 3x, the whole thing raised to the 0 power, still equal to 1. A large number, 15,001 raised to the 0 power, all equal to 1. All right, doesn't matter what the number is or what the expression is. If it's raised to the 0 power, then it's equal to 1. Next, we have our negative exponent rule. If b is any real number other than 0 and n is a natural number, then b to the negative n is equal to 1 over b to the n. Essentially, if we have a negative exponent, it's going to flip over. We're going to take the reciprocal, and then what happens is that that exponent becomes positive. Okay, so a negative exponent, if we already have a whole number part, it's going to be turning into a fraction turns back into a whole number piece. But again, we want to understand why this is. So for example, if I had like x squared over x to the fifth, if I was to work this out by hand, I would write out x squared as x times x, and x to the fifth as x times x times x times x times x. And then we would cancel out individual x's. So I have an x and an x that I can cancel out. I have another x and another x that I can cancel out. There's nothing else that I can cancel out. So in my numerator, I would just be left with 1, because remember, x over x reduces to 1. And then in the denominator, x times x would be x to the third. Again, if we go back to using our quotient rule, starting off with that x squared over x to the fifth, we would be subtracting our exponents, so I would have x to the 2 minus 5. Well, 2 minus 5 is negative 3. So again, this idea that we started off with two equivalent expressions and we solved it different ways, so then we can say that 1 over x to the third is the same thing as x to the negative 3. So again, if I have a negative exponent, it flips over and the exponent turns to be positive. So for example, if we had, let's do y to the negative 4, that would become 1 over y to the fourth. Another important concept that goes along with this is that if I had 1 over b to the negative n, so the negative exponent was in the denominator, then this would turn into essentially a whole number piece, so we would have b to the positive n. Okay, so if it's a whole number to start with, turns into a fraction turns back into what we view as a whole number piece. So now we just want to do an example that's combining the rules that we've learned so far. So when we have multiple rules, it's best to start within your parentheses first. So in here we have x to the fourth times x to the negative 3. If I worked through this by working inside the parentheses first, I have my product rule. Our product rule says that we should be adding our exponents. So what we would have here is 4 plus negative 3, which is really just 4 minus 3, and 4 minus 3 is 1. So working inside the parentheses first, we would have x to the 4 plus negative 3 gives us x to the first, which is really just x. So all of this is still being raised to the 0 power. So I'm left with x to the 0 power. Well, again, anything to the 0 power is just equal to 1. As long as it's not the base of 0. So we have equal to 1. Even from the beginning, you technically, for this problem, did not have to do all of that work, because we have an entire parenthesis or expression raised to the 0 power, so that means that it has to equal 1. So either way you want to do it, I did show with simplifying the inside first, because that is generally how you want to set these up. But if you're able to see that it's raised to the 0 power, wonderful. You can just set it equal to 1. For part B, we have y to the negative 5 over y to the negative 3. So my suggestion would be to start with our quotient rule, which means we would have y to the negative 5 minus negative 3. So we're still subtracting, so we're subtracting negative 3, which really means we're doing y to the negative 5 plus 3, which gives us y to the negative 2, and then using that negative exponent rule in order to write as the directions told us to with positive exponents, this means it's going to flip over to be 1 over and then y to the positive 2. So 1 over y squared would be your final answer here. You can actually start from the beginning of part B with flipping it over and saying, okay, y to the negative 5 would bring it down to the denominator as 1 over y to the fifth. Y to the negative 3 would be flipped over to the numerator, and then that way you would have y to the third over y to the fifth. But what you'll do is you'll end up using your quotient rule, and you'll get that y to the negative 2 either way. So it's my suggestion that you just start off with your quotient rule no matter what. So our last group of rules have to do with if we have an expression raised to a power. So if we have an exponential expression is raised to a power, we want to multiply the exponents. So for example, if I had x to the third raised to the fourth power. That means we would do x, base stays the same, to the 3 times 4, which would give us x to the 12th. And again, this should hopefully make sense, because if I were to take x to the third, times it 4 times, so x to the third times x to the third times x to the third times x to the third, using our product rule, adding the exponents, 3 plus 3 plus 3 plus 3 would end up giving us that 12. If I have a product that is raised to a power, we want to raise each factor to that power. So again, for example, if I have x to the third y squared raised to the fourth power. So inside there's a product, x to the third times y squared raised to the fourth. I would multiply the 4 by each of the exponents. So I'd have x to the 3 times 4 and then y to the 2 times 4. So that way we would end up with x to the 12th y to the 8th. Same idea as if we had a quotient. If we have a quotient that's raised to a power, raise the numerator to that power and divide by the denominator to that power. So for example, if we had x to the third over y squared raised to the fourth power, we would just bring it in and multiply, so you'd have x to the 12th over y to the 8th. We do not have any rules if we have addition or subtraction inside the parentheses, so we cannot bring in the exponent if you see a plus or a minus, addition or subtraction inside the parentheses. We only have these rules for products and quotients, so multiplication or division. So now let's just do some quick problems using the power rules that we just learned. So for A, we have negative 3z squared raised to the fourth power. Inside the parentheses, I have a multiplication, which means that I can then bring in the exponent to each piece, which means that we would have negative 3 to the fourth and then z squared raised to the fourth. So negative 3 to the fourth, we can actually do that. Again, you can use your calculator or you can multiply out negative 3 4 times. It's going to end up being 81. For here, if I have z squared to the fourth, that really means that I'm doing z to the 4 times 2, or 2 times 4, using the power rule. If we have a power to a power, we're just going to multiply the exponents. So this gives us 81z to the 8th. So again, essentially a way to look at it is that if there's no other variables and the number of your exponents look like they're kind of touching each other, they're only separated by a parenthesis, that's how you know that you're going to be multiplying them. Next we have our quotients to powers. So here I have a few issues. Definitely we have more numbers and variables that we have to deal with. The squared exponent is going to be brought into each part. Also, with that negative out in front, my suggestion is to attach the negative to the numerator. You want to either attach it to the numerator or to the denominator, just not both. So I am going to look at this as negative 2, then bring in the exponent squared. Then we have x to the third squared. The denominator then would stay 5, so I have 5 squared, and then y to the 8th squared. So negative 2 squared, we can actually work that out. It's just going to be 4. For the x to the third raised to the second power, that power rule says we would multiply your exponent, so 3 times 2 would end up being 6, so we have x to the 6th. Then in the denominator, we're going to have 5 squared is 25, and then y to the 8 times 2 would just end up being 16, and that would be your final answer. A few comments about using your calculator, since it came up in both of these problems with the negative 3 to the fourth and the negative 2 squared, is when you're typing this into your calculator, do make sure that you're using parentheses. So if you wanted to do negative 3 to the fourth, you would put in parentheses negative 3 raised to the fourth power, because what your calculator is doing is your order of operations. And if I did negative 3 to the fourth, that's not the same as negative 3 in parentheses to the fourth. Negative 3 to the fourth without the parentheses means by order of operations I'm doing my exponent first, which means that this would give me an 81, and then your answer would just be negative, versus in parentheses negative 3 to the fourth, which means I'm raising negative 3 to the fourth, writing it out negative 3 times negative 3 times negative 3 times negative 3, which gets you that positive 81. So as a rule of thumb, just always use parentheses when you're dealing with negative numbers raised to an exponent to ensure that you get the right sign. Finally, I just wanted to walk through some problems using all of the rules that we've learned. Ultimately, you want to try to think of your order of operations. So PEMDAS, you want to start inside your parentheses first to see if you can simplify. So for part A, we have a quotient inside, we have a fraction. So I would use my quotient rule inside the parentheses first with your like terms. So first I'm looking at my numbers and I have negative 15 divided by 5. Well, negative 15 divided by 5 would just be negative 3. Then I move on to my variables. So my next grouping would be a to the 4th and a to the 10th. Again, they're being divided. We would use our quotient rule and we would be doing 4 minus 10. So 4 minus 10 would end up being keeping that base a to the negative 6. And then last we would have the b squared divided by b to the negative 3. Again, subtracting your exponents, so kind of as side work here. That means that you're doing b to the second minus a negative 3, which means that really you have b to the 2 plus 3 or b to the 5th. So that way we have b to the 5th back up here. Just really realize that you're subtracting a negative. For some reason, students forget that you need to have that subtraction in there. So we performed each of these using your quotient rule, but remember, this is all still raised to that third power. So now we need to use the power rule that we learned, bringing in the 3 to each part. So we have negative 3 to the third power, a to the negative 6 raised to the third power, and then b to the 5th raised to the third power. So negative 3 to the third is going to be negative 27. Using our power rule, a to the negative 6 raised to the third, negative 6 times 3 would be a to the negative 18. And then b to the 5th raised to the third, again, we would multiply your exponent, so 5 times 3 would just end up being 15. Now the directions said to express with positive exponents. So what's important here to understand is that the only negative exponent that I have right now is the a to the negative 18. Although 27 is negative, it doesn't have a negative exponent, so make sure you understand the difference. So what's going to happen is that a to the negative 18 really means 1 over 18, or when we're looking at our final answer, that a to the 18th would be in the denominator. That means the negative 27 stays in the numerator, and the b to the 15th also stays in the numerator to get a final answer of negative 27 b to the 15th all over a to the 18th. For part B, we move into products. We have negative 5 x to the 4th y all raised to the second power, and then times negative 6 x to the 7th y to the 11th all raised to the 0. So first, again, following our order of operations, we would look in our parentheses first. Within each individual parenthesis, there's no other work that we can do. We have no like terms. We have nothing that we can multiply, nothing that we can divide using our product rule or our quotient rule. So then the next step would be to use our exponents, right? Order of operations, parentheses, then exponents. So for the first part, I'm going to have to bring that 2 in. So we would have negative 5 to the second power, then we would have x to the 4th to the second power, and then y to the second power. For my next grouping, I see that I would be bringing in a 0 exponent. Well, if I'm bringing in a 0 exponent, that means that this whole expression is raised to the 0. And remember, if the whole expression is raised to the 0, it's just equal to 1. So to save ourselves some work, I can just say that this whole thing is just going to turn to 1. You can work through it with bringing in the 0 exponent and show each part's equal to 1, but you'll just end up right back over here. So working through now what we have left, we have negative 5 to the second power, which would just be 25. Then x to the 4th to the second power, 4 times 2 would just be 8. So we have x to the 8th, and then y squared. So some people want to actually write the y to the first, have that 1 in there, so that way you can see that you're doing 1 times 2 to get the y squared. Other people just like to think, well, if I can't see anything with the y that's there, even though there is an invisible 1, we can just bring the 2 in. Also, just note that the times 1 at the end, 1 times 25, would just be 25, so it didn't just disappear. It's just that 1 times any number would just be that number, so 1 times 25 is 25, to give us our final answer of 25 x to the 8th y squared.